Ladies and gentlemen, welcome to the second series of geosynthetic webinar under the theme Design and Performance of Reinforced Soil Retaining Walls under Seismic Loading Conditions. This event is brought to you by the International Geosynthetic Society Chapter Indonesia, or INA-IGS. My name is Rifa Nurkayungyun, and it is a pleasure to act as your master ceremony in this event. Before we start, allow me to read the rundown of our event this evening. First, I will be reading the rules of the webinar. Second, there will be an opening remarks by the President of INA-IGS, Bapak Budianto Wijaya, PhD. After that, the event will be guided by Bapak Michael Dobi as our moderator to start the presentation of Richard Bathurst. The event will then continue with a Q&A session. We would like to ask you to stay with us until the end of the event because we will be doing a quiz with a very interesting prize for the winner. We will also give you access to the e-certificate at the end of this webinar. Ladies and gentlemen, for your own convenience, please put attention to the following rules. You can submit your questions for the speaker through the Q&A feature located at the bottom of the screen. The question should be in English. You can raise your question before, during, and after the presentation of the speaker. We expect you to stay with us until the end of the event to get the information you need regarding the e-certificates and also the soft copy of the presentation from the speaker. This event is also live streamed on INA-IGS YouTube channel, or you can directly go to the link s.id/INA-IGS02YT. If you have any question, please contact Sandy via WhatsApp in the number of 0282110128965. Now, without further ado, I would like to invite the President of INA-IGS, Bapak Budianto Wijaya, PhD, to give his opening remarks. To Bapak Budi, the time is yours.
Good evening, ladies and gentlemen. Welcome again to our INA-IGS webinar series, Institute Geosynthetic Society for Indonesian Chapter. This webinar is scheduled to be held every month with various of distinguished speakers from Indonesia and worldwide. For tonight, please help me welcome our today distinguished professor, Professor Richard J. Bathurst. INA-IGS is established at 15 July 1992, and we have two kinds of members. These are corporate and also individual members. All background of our members are from academicians, manufacturers, producers, contractors, etc. What do we do in INA-IGS? As mentioned earlier, we share knowledge between all parties. One example is this webinar. Another programs are biannual international seminar, educate the educators, and publishing a geosynthetic journal. We also invite participants from this webinar to join as INA-IGS member. We hope that this webinar can be one of your valuable knowledge go to source, especially in geosynthetic field. Again, I welcome you all. Thank you.
Thank you, Bapak Budi, for your kind remarks. Ladies and gentlemen, now this webinar will be guided by our moderator, Bapak Michael Dobi. Before I give the floor to Bapak Michael Dobi, I would like to remind you that you can start submitting your questions from now, during and after the presentation by using the Q&A feature. You can also add comments or upvotes if there is a similar question as yours, or you just simply like the question raised. We would like to also remind you to stay with us until the end of the event to get the information you need regarding the e-certificates and also the soft copy of the presentation from the speaker. Now, please welcome our moderator, Bapak Michael Dobi. To Bapak Michael Dobi, the time is yours.
Okay, I think we had a small technical hitch there. You couldn't hear me. Okay, let me start again. So tonight I have a great pleasure of welcoming our speaker for our webinar. And it's a great pleasure for me to introduce Dr. Richard Bathurst. I've known Richard for about 20 years. And I think the first time we met was actually in Japan at the Kyushu conference in 2001. And after that event, we also both went to Taipei, where there was a special forum organized to talk about earthquake engineering. There was a good reason for that, because it was about 2 years after the very terrible Chichi earthquake, which I'm sure many of you will remember caused a lot of damage in Taiwan. So it was a very topical subject. And with memories of that and many other memories of Richard's work, I thought that this would be a really good topic tonight to hear something about design and performance of reinforced soil structures for earthquakes. In fact, back in those days, Richard was the president of IGS. And I'm pleased to say we've met quite a few times since then. For example, the most recent was in Barcelona just over a year ago. And then previously to that was in Munich, also in Europe. And those were both IGS workshops. And I'd have to say they were, in my opinion, very successful events. I think it was a very good style of event that was organized by IGS at those venues. And one thing I'd like to tell you is that from my experience, the quality of Richard's work, his papers, his presentations is really outstanding. In fact, I'm going to read out a title here of his presentation he made at the 11th International Geosynthetics Conference in Seoul, which was called this. It was the basics of probabilistic internal stability analysis and design of reinforced soil walls explained. And this is a topic which I think frightens and worries many engineers, and including geotechnical engineers. But one thing was so wonderful was that it was the first time I understood it. Richard's explanation was so clear and so good. And in fact, at the end of his presentation, I had to stand up and tell him that. Anyhow, Richard is a professor, or certainly has been for some time, at the Royal Military College of Canada, which is in Kingston, Ontario, and I'm assuming that's where he is at the moment. So his slight difficulty is that he has a 12-hour time difference. The good thing about 12-hour time difference is that we know the time there very easily, but of course, Richard had to start quite early this morning to get ready for this presentation. Sadly for us, and possibly for Richard, he's never been to Indonesia before. So our first welcoming will be this electronic virtual welcoming to Indonesia. There's quite a big crowd of people listening to this webinar, Richard, and many of them will be from Indonesia. one reason why your topic is so important here is that, as you're obviously well aware, this is seismically a very active country. We have very long subduction zones, and earthquakes are a major issue. So I'm going to say no more now, Richard. I just want to hand over to you. I'm very much looking forward to your talk, and I'm sure so is everybody else. So looking forward to hearing from you. Thanks very much, Richard, in advance.
Can you hear me?
I can certainly hear you.
Okay. Well, then I will take that as that I can start. And I'll preface my talk by thanking you, Mike, for inviting me to give this webinar, and also the Indonesian IGS chapter for organizing it. So my presentation, as you have already heard, is design and performance of reinforced soil retaining walls under seismic loading conditions, which is a subject which is dear to my heart. And I'm happy for the opportunity to share some of my experiences with such a large number of participants. Okay, I'm pushing buttons. Bear with me here. Okay. So reinforced soil walls constructed both with inextensible steel and relatively extensible polymeric reinforcement materials have been around for quite some time. We're talking almost 40 years. In North American parlance, they're called mechanically stabilized earth walls. And it's probably appropriate to start with just a little bit of history so we can get ourselves into the context of the technologies that we're talking about. The very first reinforced soil walls were actually steel strip type. And this slide is very appropriate because it's the first wall of this type constructed in 1971.
So Richard, can you hear me?
Yes.
Can you share your screen? At the moment we're seeing you. I mean, it's good, but there's a green button at the bottom of your screen that says share screen. I think if you press that.
Okay. Yeah, we're just, you can't see my screen at all?
At the moment, not.
Okay, because before we were okay.
Yep.
Just a sec.
Don't worry, take your time.
Okay. I am going to.
I'm getting a yellow border, which means I think it's trying to share.
Oh, this is disappointing because it was.
It was. We tested
it. Everything
yesterday.
was working previously. Just a sec. I'm just okay. Hang on. I think I found where we need to go.
It might be a question of sharing the other screen.
How's that?
It's about to. Yes, perfect. Okay, I will mute again.
Okay. So you heard my opening remarks. Let me just go back to this first screen. Okay, so this is my title slides. Okay, so we're talking about design and performance of reinforced soil retaining walls under seismic loading conditions. And the slide that I was speaking to, which you couldn't see, was to mention that reinforced soil wall technologies, both with inextensible steel reinforcement and polymeric reinforcement materials, have been around for quite some time. And we're bordering on about 40 years now. In North American parlance, they're called mechanically stabilized earth walls. It's of interest to trace very briefly the history of this technology, and it's appropriate to recognize that the first reinforced soil wall with a hard facing was a steel strip type. And here's a very famous slide which shows this seminal structure in 1971. The utility of these types of structures, that is to reinforce the soil, was increased with the advent of high performance polymeric materials such as geotextiles and geogrids. And here is a slide of the very first geosynthetic reinforced wall that was constructed in North America. And it's actually a wrapped face wall type. Now the slide is pretty grainy and it's arguably not a very attractive structure, but it is historical. And this structure and many like it were constructed by placing horizontal layers of reinforcement in the ground and then wrapping them around and tucking them back in to generate a flexible wrapped face structure. And some of these systems actually were very substantial. And in 1989, a wrap face wall was used to support a prefill at a construction site in Washington State, United States. And this wall was almost 13 meters in height at that time, and it was the largest wall in the world at that time. It was a temporary structure. These type of wrap face walls are not as desirable as permanent structures because of the exposure of the wrap faces. Now we have seen hard-faced walls, and here, when you look at this structure, it appears to the layman to be a conventional gravity concrete wall in a tiered form. But the magic is that the facing units and the soil behind the facing is reinforced with horizontal layers, in this case of geogrids. And these are attached to the panels, and the geogrid reinforcement is extended into the soil behind the facings. This slide shows the construction of this type of system, and it happens to be the first prop panel wall constructed in Canada in the early 90s. And here you can see the geosynthetic reinforcement attached to the panels, extended and pre-tensioned into the backfill, and then the fill placed on top of it. And this construction continues from top to bottom. Another type of system which is quite popular is the use of modular block facing units, which are most often dry cast mortarless concrete blocks. And these are stacked, dry stacked to form a facing. And then the facing is anchored with geosynthetic reinforcement, as you see here. And what we have created, in effect, is a gravity wall, which is a composite of these concrete blocks, the reinforcement, and this reinforced zone of soil. And just like a conventional retaining wall, its purpose is to retain the soil located behind the structure. There are many types of these modular block systems around. They have different shapes. Some of them are solid, some of them are hollow. They have different connection devices in order to ensure a good connection between the facing and the reinforcement. Here is a slide of such a structure. It's quite substantial. It's almost 11 meters in height. And here you can see the facing blocks. And this wall is important because it was heavily instrumented in order to validate and give confidence to the owners of this wall that the system was performing well. And it's been in place for over 15 years now, and performing as intended. Other types of reinforcement include polyester strap type reinforcement. And here you can see the straps attached to the facing units and then extending through this backfill material. So this type of reinforcement is becoming more common in the last decade. So why are MSC walls popular? Well, like most things in life, it's a function of cost. And what you're seeing here is a plot of the cost of a wall in US dollars per square meter of facing delivered to the client. And here's some data that shows the cost of conventional, if you like, gravity walls with height. And so as the walls become higher, they become more expensive. But if you compare these structures to, for example, steel reinforced soil walls performing the same function and constructed to the same height, you can see that these systems are cheaper and the unit cost on a square face meter basis is fairly flat. And then when you replace the steel with geosynthetic reinforcement, there are further cost savings, although the difference, according to this database, is less, once you get up into the sort of 12-meter high category. So cost is very important, and it's fair to say that this technology has been driven by the manufacturers of these reinforcement products. And people like me have spent careers trying to understand how they work. Nowadays, we have sustainability is becoming much more important. And what do we mean by sustainability? Sustainability is the combined benefit due to minimal environmental impact, cost, as we saw before, but also the functionality and the aesthetics of the structure that you're constructing. And a few years ago, with my colleagues in Spain, we did a sustainability analysis of different types of structures, gravity structures, cantilever structures, and MSC walls constructed with steel and polymeric reinforcement. And this type of audit ranks different systems using a scoring that includes environmental, economic, and societal function aspects. And the higher the number, the more sustainable the structure. So if we look at the top plot as just one example, we have different heights of wall and 4 different types of classes of structures. And what you can see here is that the scores are highest for MSC walls constructed with steel and polymeric materials as compared to more conventional structures. So from a sustainability point of view, these structures are very desirable. But we're here to talk about seismic design and performance of geosynthetic reinforced soil walls during earthquake. And I would like to start my comments to say that geosynthetic reinforced soil walls have demonstrated good performance during earthquake. And this is despite some slides that I'm going to show where failures have occurred. But in general, they have performed well. This slide shows the behavior of some conventional gravity structures that suffered through the very famous Kobe earthquake of 1995. So this was a magnitude 6.8 earthquake, and peak ground accelerations were up to 0.6 G. And you can see here that these conventional structures misbehaved and in some cases collapsed entirely as the bottom left slide shows here. In the same region, in fact, along the same railway embankment that you see here, there were constructed geosynthetic reinforced soil walls. And here you see a structure, it's 6 meters in height, suffered the same earthquake. And this structure moved up to about 100 millimeters, but otherwise stayed intact. So it behaved much better than its neighbors, shown at the left of this slide. If we look at the inside of this geosynthetic reinforced soil wall, it looks like this. We have two back-to-back walls supporting a railway, pair of railway tracks. And the wall was constructed, first of all, with gabion baskets, and then these were anchored back with layers of reinforcement. And then after this embankment had been constructed, concrete panel facings were cast up against the structure. So it looks like a conventional reinforced wall system, but it's actually a geosynthetic reinforced system. Other case studies of interest are a more recent earthquake that happened in Chile, the Mali earthquake. This had a magnitude 8.8. And if you look at the seismographs or the accelegrams from this this earthquake, you'll see that the peak ground accelerations were up to 0.6 G. And it was a long duration earthquake. And after this earthquake happened, an investigation, a reconnaissance was carried out by various experts to examine the performance of different types of geosynthetic structures during this earthquake. Now, some of the performance features and characteristics of this earthquake were that in some places, as I mentioned, the accelerations were in excess of 0.6 G. A lot of places, they were down around 0.2, 0.5 G. And there was very little damage to many of these structures, including panel and block-faced walls, even for those that were more than 12 meters in height. And this reconnaissance group went back and looked at the way that these structures had been designed, and they had actually been designed for typically horizontal ground accelerations of 0.1 up to say 0.4 G, even though the earthquake itself delivered much higher peak ground accelerations. So here's an example of two approach embankments for bridges. And you can see on the left-hand side that this wall, there was a little bit of damage, but it was mainly restricted to modular blocks that were located at the top of the wall. On the other side is a concrete face panel wall, and it survived. So even though these structures had been designed for, say, 0.1 to 0.4 G, they were judged to have performed very well, particularly after ground accelerations, which were much higher. Now, other techniques have been used for these types of structures. And I just wanted to mention some of the innovations that have happened in Japan. Japan, of course, has a history, as my previous slides have shown, of having to being subjected to large earthquakes. And one technique that they've developed in order to improve the seismic performance of the backfill used in the reinforced soil zone is to use cement-treated gravel, where they add about 6 or 7% cement to tie the material together. An important question that arises when we are designing these MSE wall systems is, when do we need to carry out seismic analysis? Do we have to carry out seismic analysis for all peak ground acceleration cases? And to answer that question, it's useful to look at some experimental shaking table tests that have been carried out by others, including that shown in this slide by Atik and Sitar at the University of California, Berkeley. What you're looking at here is a schematic of a shaking table. Okay, the shaking table is the hatched line that you see here. And in the shaking table test, you put a model on this table, and then you shake the table to simulate an earthquake event. So what they did in this case is they constructed two model cantilever wall systems. They look like excavations, but these are pairs of cantilever walls. And they placed them in a volume of sandy soil. And this system that you see here on the left are cantilever walls that are quite stiff. And on the other side are cantilever walls that were constructed, as models to be more flexible. And then what they did is they progressively shook this table back and forth, increasing the magnitude of the horizontal acceleration monotonically, like increasing it uniformly. And here are some results. On the left-hand side here, we're looking at the stiff wall case. And as the peak ground acceleration was increased progressively, they measured the magnitude of the additional dynamic force that the wall was sustaining. And basically, there was no additional dynamic load measured on this stiff-faced wall until we got close to about 0.4 G, and then it increased more or less linearly with increasing horizontal acceleration. So somewhere less than 0.4 G, the wall started to feel that additional dynamic load due to ground shaking. Its neighbor, with the flexible walls, this effect of the dynamic load occurred in excess of 0.4 G. So the dynamic load was not felt for the flexible wall until a larger peak ground acceleration occurred. So there seems to be a difference in response based on how flexible or how stiff these retaining wall structures are. And this difference between stiff structures and flexible wall structures has been detected in other shaking table tests, including the ones that you see here. So a series of small scale tests were performed on a shaking table, and the difference between the tests were that some walls were gravity type or cantilever type, so they're relatively rigid, and another set of tests were done using geosynthetic reinforcement. And again, in these tests, the peak ground acceleration was increased steadily over the course of the experiment, and the amount of deformation or wall displacement at the top of the wall was recorded, and that's what you see here on the vertical axis. So the gravity type and cantilever type walls had this type of response. Deformations are increasing with horizontal acceleration. And the reinforced soil walls had the same qualitative performance, but the curves were shifted to the right. Both of this showed that the reinforced soil walls are more ductile, and the difference between these more flexible walls and these conventional structures occurs somewhere around 0.5 G. So it's not inconsistent with what we saw in those other shaking table tests that were done at California. How have actual walls performed? This is a wall that was constructed in California again. It survived the Northridge earthquake in 1994. The peak ground accelerations at this site were estimated to be about 0.5 G. But when we looked at the face of this structure, there was no evidence of distress. However, when we went and looked behind the wall, there was a disturbing crack that had formed behind the retaining wall face. However, on closer inspection and looking at the history of construction, what we found was that the contractor had originally designed the wall properly by extending the reinforcement layers to the full length, about 5.5 meters initially, but then he decided to place some subsurface utilities in this region here, which required him to cut the reinforcement. So this was not appropriate, but the point is that despite attempts to modify this wall design, the wall still performed well. So it was clear that there was additional conservatism in the design that allowed this wall to survive despite the worst intentions of the contractor. So in the United States, in the most recent AASHTO design guidelines, they recognized that there is inherent conservatism in the design of these reinforced soil systems when you design them for static. And this residual safety is enough for these walls to behave well if you then subject them to a peak horizontal ground acceleration less than about 0.4 G. So for typical structures, you don't have to worry about seismic design greater than 0.4 G. But there are important caveats. Okay, you can't use this rule if you have soils that are going to liquefy, or you have sensitive clays, etc. If you have another structure which is in very close proximity to your wall, well then you have to consider seismic. And walls that have corners or short radius turns, then you do have to consider seismic. But this is better than the old days when AASHTO specification said you had to do seismic design for all cases. Here we have a little bit of room to maneuver for conventional structures. When we design these walls, we start first by recognizing what are the limit states or modes of failure that these walls will have to survive. And for those of you who have done this type of design work, you will recognize that we identify these limit states or modes of failure as falling into external categories, internal stability categories, and facing stability categories. And we design for these modes of failure for static. And what we have to do is we have to then consider the additional forces that are developed when seismic loads are imposed on these systems. So if we consider first external base sliding, the question is, well, what is the additional force that will be exerted on this composite mass as a result of horizontal ground accelerations or even vertical ground accelerations. And the method that first comes to mind is the so-called Monabio-Cabby theory approach. Now, the Monabio-Cabby approach is simply the conventional or classical Coulomb earth force or earth pressure approach, in which additional horizontal inertial forces and potentially vertical forces due to seismic acceleration are included in the stability calculations for this critical wedge. And if one goes through the mathematics, you can relate the total active earth force, okay, this is due to static plus seismic, in a classical active earth pressure formulation in which KAE replaces the active earth pressure coefficient that we recognize from classical active earth pressure theory. So this is sort of the first level of analyses that we might carry out for these type of systems. And of course, the magnitude of this force is a function of the geometry of the wall and the back slope and the friction angle and the orientation of the face of the wall. Now, one of the outcomes from using this Monabio-Cabby approach is that if you calculate the active earth force as a function, and you see here on the horizontal axis, the horizontal coefficient of acceleration, what happens is that PAE increases with KH, not unexpected. But the magnitude of that value is also critically dependent on things like the back slope angle. And if you carry out these calculations yourself using the closed form solution that I just showed you, what you find is that you may not have a solution. And this equation will blow up at high horizontal ground acceleration values, particularly when they're coupled with, for example, a large back slope angle. So this equation, the utility of this equation is somewhat limited. Fortunately, it's about 0.4 G, which you may recognize as being sort of the threshold when we have to think about serious seismic design. Now, other modes of failure that one has to consider, and this is true of whether we're talking about static cases or we're focusing on seismic cases, and that is to ensure that your reinforced soil wall structure, such as the one that you see on the left-hand schematic here, is not carried away by a larger, slope type instability. The client's not going to be happy if the wall is intact, but somewhere downslope. And the conventional technique to carry out this type of analysis are classical method of slices techniques. And here, these are solutions using the Spencer method. And these systems easily accommodate, including the horizontal force that is due to seismic acceleration in this method of slices. These programs, again, for static and seismic conditions, also have the advantage of allowing the designer to examine other modes of failure, such as these composite type mechanisms, where a critical failure mechanism passes through the retained soil and then also through the reinforced soil zone. And these types of programs are available. They're commercial programs. The example that I show here is from a company, Rock Science, which many of you may be familiar with. Another approach that we can carry out, and in particular, this is sort of starts the next level of sophistication of analysis, are so-called Newmark sliding block methods. And the cartoon that you see up here in the top right-hand corner symbolizes or represents a reinforced soil wall. And this wall can be expected to move if the magnitude of horizontal acceleration at the base is of sufficient intensity and duration. So the Newmark sliding block method involves, first of all, finding what would be the critical horizontal acceleration to create or compute a factor of safety of 1 against base sliding. Once this critical acceleration has been calculated, then it's superimposed on top of your candidate accelerogram for the site. Okay, and everywhere where the critical acceleration is exceeded, integration is carried out to calculate what is the velocity of this block over that interval. And then next, the velocity response outcome that you see here is integrated again, and this gives us the displacement. So what this slide shows is that subject to this accelerogram, we can expect this block to walk or displace with time according to the trace that you see here. And this is very important because it gives you a performance appreciation of this wall that you can't get when you just do force-based equilibrium analyses, for example, method of slices, for example. So this is one technique. Now let's look at internal sliding. We want to make sure that the reinforcement remains intact. There's no tensile failure of the reinforcement during operational conditions and including seismic, no connection failures between the reinforcement and the facing. And the reinforcement doesn't pull out behind this theoretical active wedge that we've seen before. This is called pullout. And the technique that's used in are of different types. The first type uses the so-called simplified tieback wedge approach. And here what we assume is that under static loading, we have an active wedge, and each layer of reinforcement is responsible for carrying a portion of the static pressure distribution, which is computed using active earth pressure theory. An active earth pressure theory says that the lateral earth pressure will increase linearly with depth from the top of the wall to the bottom, according to this triangle that you see here. And so we just integrate up over each contributory area the lateral active earth pressure, according to this formula you see here. Here Z is the depth of the reinforcement, gamma is the unit weight, and Ka is the active earth pressure coefficient. And this is adapting classical earth pressure theory to reinforced soil walls. And we design to ensure that this active earth force is less than the allowable tensile capacity of the reinforcement, so that it doesn't rupture or strain excessively. And this load has to be less than the pullout capacity of the reinforcement in the pullout length of the reinforcement in the resistance zone. And finally, this load has to be less than the load that can be carried by the connection. So that's the classical simplified tieback wedge approach. Now, what has happened recently in the United States is the distribution of load or pressure that has to be carried by each reinforcement layer is now calculated using the stiffness method. And the stiffness method, as the name implies, relates the load and the reinforcement to the stiffness of the reinforcement, not the strength. And this method shows that the distribution of load doesn't increase linearly with depth as we had in the previous slide. It's sort of bilinear. And the calculations are otherwise similar, although this method introduces a number of empirical coefficients that take into consideration, first of all, the stiffness, as I mentioned, but also the flexibility of the facing and similar factors. And again, the design, you have to ensure that the maximum load that you calculate is less than the allowable strength of the reinforcement, pull-out capacity, and the connection performance as before. And this method provides more reasonable estimates of the reinforcement load. The simplified method, which was used in the United States before this year, or last year, sorry, was excessively conservative. So this is for static. So what do we do for seismic? Well, for seismic, we simply add to the static load in each reinforcement layer an estimate of the additional dynamic load, which is developed due to seismic loading. And the way this is done is the active zone is assumed to develop an additional seismic load, which is the weight of this wedge times a coefficient of horizontal acceleration. And then this additional seismic load is distributed evenly to all of the layers of reinforcement by simply dividing it through by the number of reinforcement layers. And then these two are just added together. So that's, the premise of this method for calculating the internal distribution of reinforcement loads in MSC walls or geosynthetic reinforced walls under seismic. How do these methods work? Well, I just showed you one treatment of the additional horizontal load due to horizontal shaking. And we've done shaking table tests, and we've looked at different methods that folks have used to calculate this additional dynamic load. And basically what we found is this type of superposition technique that I showed you before does a reasonably good job, at least in our shaking table tests, to match the measured tensile loads in these reinforcement layers under simulated earthquake. Here's a slide showing some shaking table tests that we have performed in the past. Here you can see a modular block wall, and here's a picture of our shaking table at RMC at that time. And I'm going to show you a movie. It's a little bit grainy, but what we did was we just progressively increased the intensity of the horizontal shaking at the base of this table, and the model is moving in the direction of this cross section you see here. And as the shaking gets more and more intense, you can see that something bad is happening as the blocks in the top of the wall over the initial reinforcement layer start to walk out as the peak ground acceleration for this wall was increased. And this was a fairly intense simulated earthquake. There's a lot of audio with this particular slide, which I don't want to share with you. So here you see, looking up the face of that same test after the test was over, and you can see some of the blocks have shifted. And this speaks to the need to ensure, particularly at the top of these walls, that you have sufficient connection capacity. And this is easily done either by, constructing with specially constructed walls that have very good mechanical connections, or other techniques that people have used to tie the top of these walls together. I had the opportunity to do a reconnaissance of retaining wall performance after the El Salvador earthquake in 2001, and this was quite a significant earthquake. It did a lot of damage, and there were many conventional gravity wall structures like the one that you see here that failed, absolutely completely. And this was a full-scale laboratory for me to go down and see, well, how did different types of retaining walls behave during this event? And here's a modular block wall that didn't fall down, but it had some cracks on this corner. Okay, and again, you may recall in AASHTO they say, pay special attention to these outside corners. But on the other hand, there were other walls. In fact, this one was just across the road, and this one had actually been better designed, and this one behaved perfectly. And it was because it had been designed for seismic, using seismic design recommendations that I was involved in at that time for the design and construction of modular block walls. Now here's a modular block wall again in El Salvador, and this one has suffered a catastrophic failure at the top of the wall. But there's a backstory here which is very important, and that is that this wall was originally designed to about the elevation at the bottom of this red arrow that you see here. And the owner of this wall at that time was so enamored and so happy with this wall, he told the contractor to make it even higher, but let's save some money and not buy that plastic stuff. And so they built the wall higher, and the earthquake happened, and the unreinforced part of that wall fell out, as you see here. Lesson learned. The next level of sophistication for design and analysis of reinforced soil wall is to use dynamic finite element modeling or FLAC modeling, and we've done a lot of this. The problem is that it's user beware. You don't want to do this type of analysis unless you have some experience, because these types of sophisticated models will always give you an answer, but whether it's a reasonable answer or not is a decision that has to be made, preferably by people that have this type of experience. One performance feature of these types of structures, which is often not mentioned, is the influence of the wall fundamental frequency. This is the natural resonance that all structures have. And this can actually be explored most easily using numerical models, such as the FLAC model that I showed you in the previous slide. And here are some interesting outcomes. Here we see a reinforced soil wall, and this numerical wall was subjected to different frequencies of loading. So it had the same peak ground acceleration, but we just went through a suite of different frequency content. And we measured, or we calculated, the deformation of the wall, maximum deformation. And here it's just normalized with height of wall. And so what we found was that there was a a critical frequency where this wall came apart numerically. And this is about the natural frequency, occurs at the natural frequency of these structures. And it's interesting because in North America, sort of typical wall height's about 6 meters. In some places, the typical input frequency or predominant frequency of earthquakes is in the vicinity of about 3 hertz. So what this means is that if you had a long duration earthquake with a predominant frequency in the range of 3 to 4%, the wall may misbehave. And this is something that you can't catch using conventional, force-based design methods, such as those that I've showed you before. So this is something that has to be looked at. Another question that is often asked, what is the influence of reinforcement stiffness? Geosynthetic materials have stiffnesses that typically range from about 500 kilonewtons per meter to 2,000. And steel reinforcement materials can be up around 70,000 kilonewtons per meter. So I'm talking about steel reinforcement. So again, we have carried out numerical modeling where we kept the peak ground acceleration and the frequency the same for different walls, differing only with respect to their stiffness. In this region here, these are the loads in the reinforcement, or normalized loads in the reinforcement, that are shown to be quite low at the end of construction. But then when we applied a seismic excitation, you can see the additional load that's going on being carried by the reinforcement layers. And the takeaway from this slide is that as the reinforcement gets stiffer and everything else is the same, then you will generate more load on a reinforcement layer if it's a very stiff material like steel compared to a geosynthetic reinforcement layer. And this goes back to the idea that one of the advantages of these polymeric reinforced soil walls is they're more ductile, okay, and more forgiving of these dynamic loads generated due to earthquake. So the question then is, where can I get help? What guidelines are out there to assist me to carry out design for earthquake? Now, there's a couple of places. One place is ICE has published a handbook of geosynthetic engineering. It's now going into its 3rd edition. And this handbook examines all types of geosynthetic applications. And one chapter, which I had the privilege of writing, is focused directly on the design and analysis of geosynthetic reinforced soil walls and slopes. So this is a good reference. Other places to look are on publications in the U.S. In the United States, the Bible for the design of steel and geosynthetic reinforced soil walls resides in the LRFD design specifications shown at the right here. So the Americans use, and the Canadians use, a load and resistance factor design approach. But these specifications provide details and commentary on how to design both for static and seismic. Now, it's quite expensive. I can't even afford it. But there are supporting documents published by the Federal Highway Administration, including the one that you see here, that are actually free. You can download them from the web. And these provide detailed and well-presented explanations of how to design these systems, both again for static and for seismic. Indonesia, of course, has tragically suffered from the effects of tsunami. And I like to say a few words about geosynthetic reinforced structures and their performance due to tsunami. And I'll start with this slide here. This is a photograph. Now, it's a steel strip reinforced soil wall, but there were similar walls of this type that were inundated due to the tsunami, run up during the infamous Japanese earthquake and tsunami of 2011, the one that we associate with the Fukushima disaster. And this wall survived this inundation event, as you can see by the dashed line here. Some walls didn't perform as well. This is a large reinforced soil wall that was right on the coast, so it felt the full force of the tsunami. But the way it really failed was due to scour at the bottom of the facing, as you can see here, and also when the tsunami wave receded, okay, that washed out a lot of the soil behind the wall, and also put some additional parasitic loads onto the reinforcement. So it wasn't the onset of the initial impact of the tsunami, and it wasn't the earthquake. It was the effect of the tsunami retreating from this particular site. And this problem of cyclic water loading on MSE walls is of interest to Japanese practitioners. And myself and my dear friend and colleague, Dr. Yoshi Miyata, have been able to analyze the behavior of full-scale MSE wall structures constructed at the Public Works Research Institute in Japan. These folks are amazing. They build these structures, and you can see the size of them. That's me. Okay, and I'm pretty large, but you can see the walls much bigger. And the walls are subjected to different types of loadings. And again, this is just one example. Here's you can see the cross section of this retaining wall, layers of reinforcement attached to incremental panels. And then what was done, in front of the wall, the water was introduced, and so the water level was increased, and then it was drained, increased, and drained. And while this was going on, the behavior of the fill and the loads in the reinforcement layers were recorded. And a practical outcome from this study and other walls of this type was that, as long as the soil behind the panels is well draining, and as long as you place a geotextile against the back of the wall, a suitable porous geotextile behind the back of the wall to keep the soil from running out between the joints, these walls will perform adequately. And so this was a takeaway from this type of full-scale testing. And there are more tests of this type that are underway in Japan as I speak. Another application of geosynthetics in Japan has been the construction of coastal countermeasure protections. So one of the problems with these tsunamis is that they can travel great distances inland. We're talking kilometers. And so one way to mitigate against that inland inundation is to build these berms. And these berms are constructed in such a way that the energy of this flow is dissipated on the downstream side of this berm. So these berms are constructed with concrete faces, cement treated soil, and then and geogrid reinforcement. And here you see these are example structures constructed in Japan. They have different slopes and this type of thing. And here you can see the reinforcement inside. And then to maintain the integrity of the connection between the reinforcement and the concrete facing bits, special blocks with special connections to the geogrid reinforcement were designed. And they have taken these structures and scaled them down and placed them in hydraulic flumes. And this is what you see here. So here you can vaguely see the outline of one of these models and see whether they survive and see what effect they have on the travel of that tsunami past the shoreline. So this is an interesting application of geosynthetic reinforced structures. Just a second. Okay, so here you see, this shows the same general approach, but it's an embankment supporting railway tracks. But you can see the upstream concrete face, which is impacted by the tsunami. So. Another technique that has been used to mitigate seismic induced loads on MSE walls are the use of seismic buffers. So what is a seismic buffer? It is a compressible inclusion which is placed between a rigid wall and the retained soil. So here you see a schematic, and you can see that this is a rigid wall, and then this is our buffer. And these were originally developed to reduce the lateral earth pressure behind rigid walls by letting the wall composite, that is the buffer, deform and allow the soil behind the wall to reach an active state, because we all remember that the active state is the state which develops the minimum lateral pressure against a rigid retaining wall structure. So this buffer encourages an active state to be developed. Now this technique was originally proposed for static loading, but can be extended to dynamic loading. So it's not just getting to an active state under quasi-active conditions, but it can also conceptually act as a buffer to reduce dynamic loads. And the material that is best suited for this purpose is polystyrene or geofoam. Okay, we call it expanded polystyrene geofoam, so EPS. And here you see a picture of this material after it's been manufactured. And many of you may be aware of this material because it's the same material that's been used as a lightweight fill for many decades. The first example of an EPS seismic buffer was actually occurred in Canada, and it was used in conjunction with deep basement walls at the location of a very tall building in Vancouver. And the problem that the structural engineers were faced with is that during an earthquake, additional horizontal loads are developed against rigid reinforced concrete wall structures. And to carry those additional load requires more concrete and more reinforcement. So the idea was, how can we reduce those dynamic loads? And they were able to show the geotechnical engineers were able to show, at least theoretically, using a FLAC model, that you could reduce the seismic loads by up to 50% by putting in this compressible seismic buffer. So numerically, there was evidence in support of this technology, but what was required was proof of concept. And we did that by carrying out some shaking table tests at RMC. And what you see here is a schematic of the model arrangements that we used. So the first thing you see here is the shaking table. Again, it's a platform that allows us to simulate ground acceleration in the horizontal direction. And it's the models were built in a box. And at the green shaded area there is our simulated rigid retaining wall. And in front of it is a column of this compressible geofoam. And the green highlighted area here is sand. So we shake this thing back and forth. And while we're doing that, we can measure how much the foam compresses, and we can measure the horizontal loads acting on the rigid wall to see whether the buffer is reducing those loads or not. And so we did one test with a control wall, that means no foam, and then we did 6 other tests where we played around with the density of the geofoam buffer material. And this photograph shows you shows what the buffer material looks like. So this is white stuff is the geofoam, behind it's the rigid wall, and it's a fairly substantial model. And the soil fills the box on our shaking table behind the geofoam buffer in this open area that you see here. So that was filled with sand. And then we had 6 buffer tests and 1 control test, and we played around with the density of the foam, either by purchasing foams of different densities, but also by simply cutting out portions of the foam inside the buffers to reduce its macro density even further. So this changed its modulus, okay, and we kept the stiffness the same. And here you see the results. So here's a schematic in the top right-hand side that shows the force acting against the wall. And we subjected each of our models to increasing peak ground acceleration. Okay, and that's what you see on the horizontal axis. And then we just measured the force acting on that rigid wall. And what the results show is that as the acceleration increased, okay, the load on the wall always increased pretty well. Okay, but as the buffer density went down, as it became more compliant, that load was less. So you can see there's quite a substantial difference between what happened at the top of for the stiff, the unreinforced wall or no buffer wall compared to the ones below. And this benefit, the relative benefit was the same as what we observed when we placed the reinforcement prior to seismic shaking. So a 40% reduction in wall loads, and that's not too bad. It's close to the 50% that was predicted using the FLAC design model for the Vancouver project that I mentioned earlier. So what we did next is we used a FLAC model to carry out parametric analyses to come up with design charts that could be used for actual field cases. And we compared the predicted forces using our numerical model to experimental models. Okay, so as the experiment progressed and increasing ground acceleration was applied, wall forces, what we measured, went up, and perhaps miraculously, our numerical model was able to pick up and give a reasonable prediction of what we actually measured. So that meant that we could take this model and scale it up to field scale and carry out parametric study. So we came up with a synthetic excitation record, which is this variable amplitude that you see here. We are able to change the frequency of the excitation and its magnitude. And from this, we were able to quantify performance parameters for these buffers. And one parameter that we developed was called the buffer stiffness. It's like a spring stiffness. And it's quite simply the ratio of the elastic modulus of the buffer and its thickness. And then the measure of its efficiency to reduce loads was quantified by isolation efficiency, which is basically for the same conditions. It's the difference between the peak force for the rigid wall and the peak force for the treated seismic protected wall. So what you want to do is you want to have this number as large as possible. And at the end of the day, we came up with design charts that show the efficiency of the seismic buffer versus its stiffness or buffer stiffness. And we did this for walls of different height and different combinations of predominant frequency versus the natural frequency of the walls. And basically what we found is as the buffer stiffness goes down, the efficiency goes up. And from these charts, we are able to, or from this work in general, we are able to demonstrate physical proof of concept. And we identified the seismic buffer stiffness as a main parameter. And what we were able to recommend to designers is that if they can keep this buffer stiffness value to less than about 50 meganewtons per cubic meter, which is not hard to do because you just have to adjust the thickness of the buffer and its stiffness to get in this range, you will generate significant reductions in dynamic load due to earthquake. And there are a number of papers that have been written on this that you can find. And I'm happy to say that this technique was actually used at the location of a reservoir in Vancouver. So this was a storage reservoir, which was ultimately capped with a roof. But the reservoir walls were rigid reinforced concrete type, and it was girdled by this EPS seismic geofoam material in order to reduce potential dynamic loads due to earthquake. So it's actually been used in practice. And again, if you're interested in this technology and some of the other slides that I may have shown you, there's a bunch of papers that you can just download from my website. So I think I'm slightly over the time that was allocated to me, but I've run out of slides. So I will stop here and entertain questions.
Well, Richard, can you hear me? I want to make sure that.
Yep.
Okay. Well, the first thing I'd like to do straight away is to thank you for what was an incredibly good presentation with a lot of really first-class material. And not surprisingly, you've generated a lot of questions. And currently, I see there are 29 of them. I don't think we can handle 29 questions tonight. What we'll do, we should get a recording of all the questions and might send them through to you a bit later on. But I thought what would be a good idea, I've been scanning over them, would be to concentrate on the ones that are talking about the earthquake case. Some of them are not aimed at earthquake, but quite a few of them are. So I've opened the Q&A at the bottom. You can probably do the same, unless I think that's probably the best thing. Can you do that? And then if you do that, I guess we should be able to read the questions. If you
yes,
open
I can see them.
Me too. I can see them too. So I think I don't know if I can share my screen. No, I think probably leave it like this. But I've scrolled to the bottom. It's not because of any particular reason, but I've been looking from sort of they did actually start arriving from the top downwards.
Yeah. Okay.
What I think, because of the time available, can I recommend that you scan, start at the bottom, and then there are some very good ones aimed more at the seismic design aspects, and a lot of them complement your presentation material. I can certainly pick out a few which I think are instantly important to talk about, but maybe if you want to pick out a first one, I'll have a look and then find the next one.
Okay. Well, the bottom one on liquefaction is a good question, and I'll just preface my answer to that bottom. The question was now it's disappeared. Just a sec. The question that I'm answering is.
Hang on, it's because it's collapsing itself. Hang on, I think. Hang on.
The question was related, I think, said something like what walls are best for liquefaction prevention. The point is that anything that you do to prevent the collapse of any type of retaining wall due to liquefaction applies to geosynthetic reinforced or even steel reinforced soil walls. The mechanics of the problem and the threats to the structures due to liquefaction remains the same. So you're not going to make a wall more resistance to liquefaction just because it's an MSC wall.
No, right, okay. I think the questions are still coming in, so the list keeps kind of jumping, but I thought there's the liquefaction one. Can you see that one? It has a green name in the colored box.
That's the one I just tried to.
Yeah. The one above is an interesting one. If the one from James Utomo, which has a kind of purple color. Can you see there's some
yes.
guides state about the reduction factor applied to it's the PGA reduction question. Can you talk about that?
Yes, and I didn't get to that, but if you look at the AASHTO design guidelines, they have recommendations for how to treat the peak ground acceleration. So if you have a structure that doesn't move, then you have to use, if from memory, you have to use the full peak ground acceleration. But if you have a structure that can move a bit, it's more resilient, then you can factor that peak ground acceleration down. And those rules are written quite clearly in the current AASHTO design approach. So the thing is that because these MSC walls that we're talking about are more flexible, there is they can use this factored down peak ground acceleration value, which of course leads to more cheaper design solutions.
Can I ask a supplementary question to that, Richard? It's a question of
sure.
Mechanisms that actually intersect the reinforcement layers. If you have a significant deformation on those mechanisms, it seems to me that you might rupture the geogrid. So would it be a good idea to take into account a large displacement on that kind of mechanism rather than, say, just sliding on the base?
Yeah, you have to analyze all potential failure mechanisms. So you are talking about the sort of composite failure mechanism as opposed to just external sliding at the base.
Yep. Okay. So, should we carry on then up the list here? I don't know whether you're seeing mine or not, but there's a question there about it says geotextile selection in an earthquake area with a soft soil structure. Well, I guess soft soil in the foundation. Any particular criteria or special requirements there? Soft soil foundations and earthquakes.
Well, I think that to do calculations where you have a soft foundation, again, there's nothing really different in the mechanics of what's going on. The advantage of these geosynthetic structures is they tend to be more flexible and more forgiving of differential settlements that can happen. But this is true of static loading cases and also earthquake loading cases.
Yeah, okay. I think it's absolutely true. There's another one. I don't know if you're seeing what I'm seeing. There are a couple of names with the green outline on the initials there. But there's a question here about the seismic buffer, because that was a really interesting piece of information. So are you able to see that question, Richard? From Mr. Avik Kumar Mandal?
Yes.
Right. Yeah. Yeah. Oh,
whoops! Then it just moved.
Yeah, I think it's because new questions are coming in. But
yeah,
anyway,
okay.
I'll put it back in the middle.
Yeah. Okay, so okay, so this is this question relates to whether you have a hybrid wall in which you have the seismic buffer there plus the reinforced soil as we have described for MSC walls. We've actually done experiments, shaking table test experiments, which I haven't got around to actually writing up yet. But what we did is we did exactly that. We built a large model of an MSC wall, and then between each reinforcement layer, okay, we put a geofoam column, and so the reinforcement was just going straight through to the facing, and the buffer was placed sort of the same way that you would put a vertical drainage layer directly behind the facing.
Interesting. Yeah. Just above there, there's a from James Utomo again. There's a good question there about what you do about poor water pressure when you say you have water involved in your analysis for the earthquake condition, and taking into account water pressure at the same time as seismic loads. I think that's always a good question.
Yeah, well, hopefully, and maybe it's more of a challenge in Asia than it is in North America. But in North America, the specifications for the backfill require that it be, quote unquote, a good draining material, so that water will not accumulate. And proper design is that any water that comes in proximity to these structures is directed away. I think if you had a fully saturated backfill and then you had an earthquake, then you possibly could get problems of excess pore water pressure developing, but it would be a bad design in the first place. Okay, you shouldn't allow. You should design these things with materials that prevent water from accumulating behind the facings in all cases.
Yeah, yeah. There's an interesting one there about because you mentioned the use of cement in the Japanese approach. A question here whether that makes the soil mass stiffer, which maybe has some negative effect.
Yes, that application that I showed there. If you scrutinize it long enough, you'll realize that what it is that it's the fill which is used in the for the approach abbankment to a bridge deck and abutment. So this all of that material will be up in the air, so to speak. So presumably there's less chance of water accumulating in that structure.
Yeah. Okay. I'm just trying. There was some other ones I picked up when I was going through, which I thought were really interesting. There's another one there on the effect of water pressure. I think you've already covered that one. Subjected to seismic actions. Talk about the effective design, retaining wall, which types of produce the best. I think really this question, you see it there, there is 1 and 2 there. Please elaborate more details on the most critical aspects, especially designing the reinforced soil retaining walls to withstand the dynamic loads subjected to seismic. I mean, I think any important details to be taken into account. I mean, you mentioned the issue about connection strength, especially at the tops of walls and stopping blocks falling off. I think that was a good point.
Right.
Any other details that you think are worth mentioning? If you think about that, I'll look at the second part.
I think that's the main takeaway lesson that we have seen. Yeah, that's the main lesson. I mean, the thing is that these MSE walls basically are more forgiving in the first place, even without seismic design.
Yeah. I think the second question there you really dealt with already. Oops, we have unfortunately we have questions. We got 34 questions. Every time one comes in, the thing jumps. Although I think we're probably getting. I'm not going to subject you to too many more of these because I think we're coming towards the end of the time. But I'm just looking to. I know there are 1 or 2 other really nice ones. Very capacity. Please explain the subgrade bearing capacity criteria so that the MSE walls can stand upright in the presence of the earthquake. So to do with the foundation bearing capacity. Anything special to say on that one, Richard?
Well, first for static, of course, you treat the reinforced soil mass as an eccentrically loaded footing, and for any other footing in geotechnique which is subjected to seismic loading, you would apply the same approach, because the soil really can't tell the difference between your reinforced soil composite mass and a large footing. So any wisdom that is used to design for the bearing capacity of large footings applies also for MSE walls. It's just, again, they tend to be more forgiving, and the contact pressure between the base of the reinforced soil mass and the foundation is much more even. That Meyerhof thing that people use, they do use it for design, but we have found that the actual distribution of contact pressures is not as aggressive at the bottom of these walls as you would expect for a rigid footing case.
Yeah, that's interesting. Yeah. Perhaps just 1 or 2 more, but there's one here from Pak Go Chi Leong. Pak Go, he was our previous president of our chapter here, and then basically he's got something on the water pressure one there, but I think it's the middle part which I think is particularly interesting, especially also for me, is about vertical acceleration, taking that into account. Oh, yeah. It's certainly something that I've spent a lot of time looking at, and I've got some fairly strong views on it. But what are your thoughts about the effects and taking into account vertical acceleration?
Right. So you may recall from that Manabio-Cabby slide that I showed that obviously you can have a vertical and a horizontal inertia for your critical mechanism. So there's a couple of things. First of all, the chances of a vertical horizontal acceleration, peak horizontal acceleration, and a peak horizontal acceleration and a peak vertical ground acceleration happening at the same instant in time is remote. The usual practice is to do your analysis using the horizontal acceleration, and then you can do a few checks just looking at the effect of the vertical acceleration. But normally it's the horizontal acceleration that's the problem, because it's acting in the direction where you have a relatively free surface, which is the face of the wall. Now, so anyway, that's my opinion on that issue.
Oh, well, thanks. No, it's interesting what you have to say on that one. Just to let you, I mean, I spent a lot of time looking at the earthquake records from one of the very strong New Zealand earthquakes recently, where they published extremely good strong motion records. And I looked specifically at that point. Did we get any peak vertical and peak horizontal at the same time? And I have to say, on the whole, no. But there were some cases where they were right on top of each other. And I felt what you should be doing is to look at a combination of the two. So in fact, what you're looking at is a vector, is a direction of the acceleration, which, so you don't put the two peaks together, but you've got to recognize that they do come together, and it's like a rolling motion with a kind of vector. And that's with all the current software we have, it's very quick to look into that particular case.
You can do it, but the thing is, you'll often get a super critical situation if you get them, at the wrong time. The other thing to look at too, and this is, when you start talking to experts, is they'll also look at, what is the distance between the epicenter of the earthquake that caused this distress and your structure. And so if you happen to be sitting on top of this, the source of this earthquake, you could conceivably have very serious vertical accelerations. But generally, as you get further away, it tends to be mainly the horizontal component that's most predominant.
Yeah, agreed. Actually, it's interesting. If you look at the records from Christchurch, it's exactly like that. The dominant vertical is close, of course, and it switches around as you go further away. That's very clear. So I think where I'm getting a signal. Okay. We haven't got a lot of time left, let me just see if we can find there's certainly a lot more questions here. But I want to try to concentrate on those. Here we are. Okay, so actually this is a good question, because certainly here in Indonesia, we don't have the luxury of being able to use nice granular fills all the time. On some islands there aren't any. They're too expensive to bring in by ship or something. So we're often building with finer fills, although we have some very, very forgiving fine fills here. Some of the volcanic materials derived from volcanic debris and so forth actually produce some rather good materials, but they are clays. Any particular comments you'd have to say on that in relation to earthquake?
It is possible. The Japanese have the same situation, and they have been able to build these structures with backfill materials that would not be acceptable, for example, in North America, where we are blessed with these high quality fills. So it can be done. The thing is that you have to pay particular attention to the issues of water, because if you do have fine grained materials, then you do have the potential for softening, for example, of the backfill soil, which can have a long-term effect on the performance of these systems. So it can be done, but requires greater care, particularly during construction.
Yeah, I think that's really good advice. I think we got a couple more minutes, so I've got to give you a rest soon, Richard. You've really. No,
I'm fine. I just got up. I'm ready to go.
Oh, you just got up, of course, yeah. I just want to hear about. This is more about choice and appropriateness of different kinds of facings, panels versus blocks versus other styles of facing, particularly for the earthquake design case. Whether there's any preference or what your experience would be on that.
I think it's there are advantages and disadvantages. One advantage of block face walls is, again, they're a little bit more tolerant. They are often constructed with just a simple gravel pad or maybe a mud mat. When you use concrete panel walls, you invariably have to use a more substantial footing. So that's adds more cost. And with the modular blocks, again, the top blocks, you got to be careful. But I'm not sure I could say that one facing type is better than another. I mean, I showed you a slide from the Chile case, and you had two walls side by side. They both behaved well. They could have done a better job at the top of the modular block wall, but they were a full-scale field experiment that showed that both types can work.
Yeah, no, actually, that was a good photograph. That was a really good example, I think, of having those two styles of wall side by side. Okay, I'm going to subject you to one more because I think it's also quite a kind of an important one. It's about dimensions, criteria for limiting height of MSE walls, and the if you like the ratio of height to width, with particular reference to seismic design cases.
Yeah. Well, first of all, when it comes to height of walls, the analysis will tell you if a wall's too high. I think what happens is it has a lot to do with the confidence of the designer or the jurisdiction that you're building the wall in. I know that, for example, in the United States, there are some departments of transportation that say, no, you can't go more than 10 meters. And that's only because, the experience with higher walls is less, and, public officials tend to be very conservative. But I don't think there should be any limit. There are some examples, for example, in the States where they have built walls up to 40 meters in height. Now, they're tiered walls, so they have offsets in them. But I don't see a magic limit for these things, even though most walls, in my experience, are probably 7, 8, 9 meters in height. In terms of the width of the reinforced soil masses is typically taken about 60 to 70% of the height of the wall, and that's sort of a empirical rule that has been around for a long time. It gives you a margin of safety because people have found that it gives you added protection. But really, the length of the reinforcement is controlled largely by the sliding resistance at the bottom of a wall. And you only get to 60 or 70% of the height of the wall if you have a low friction material around 30 degrees or so.
Yep. No, I think that's certainly the case. I certainly agree. I mean, we've got some quite big structures built. They're generally tiered structures, built even for earthquake zones, and providing you've done all your mechanics, you've got your calculations done well, there should be no big issue. So, okay. Well, Richard, I think this is you've really imparted a huge amount of your knowledge and experience to a huge audience. We're still sitting at 360 people on this forum, and we also have a live feed to YouTube, so that could be another 50 or 60. I don't know what the numbers are there. So a huge number of people have benefited from your experience. They've seen the incredible quality of the materials and the sheer amount of data you've presented tonight, and likewise, some of that I've seen before, but not that much. I'd have to say there was so much new information there. It was nice to see Fumio's old slides from the Kobe earthquake again. Right. But so much excellent data and information and so forth, and we'll as you've agreed to, we'll make a PDF copy of in some way and allow people to have that as a handout. I think you're happy with that. Yep. So I'll get in touch with you about doing that. And I just thank you again for all of the work you put in to producing this. It's so relevant in Indonesia, where we're one of our world records is probably the length of our subduction zones and the right. strength of some of our earthquakes, and people have to take it seriously. So I think just one more big thank you, Richard. That was a really excellent presentation. I think you can now stand down. Please, if you want to stay logged on, there's a little bit more to go on, and there's the quiz. Maybe you got yourself a cup of tea or something there. But I would also just like to say once more, thanks very much. Fantastic. And hopefully be in touch with you again before too long.
Thank you very much, Michael. Thank you everybody for attending this webinar.
Okay, once again, thank you, Richard Bathurst, for your excellent presentation, and thank you also to Bapak Mike Dobi for guiding the session. Ladies and gentlemen, we invite you to the upcoming webinar under the theme Reliability-Based Optimization for Prefabricated Vertical Drains Improved Ground. We'll be speaking in this webinar is Doctor of Engineering Lucky Handoko. You can register at the link s.id/webinar INA-IGS 03. Next, I would like to invite all of you for the chance to get the very interesting prize by joining a very short game we have prepared. You can now directly go to your browser, whether it's on your phone or on your PC, and type menti.com. You have to type the code number shown on your screen or also there in the chat box. The code is 2468967. Once again, please go to your browser on your phone or on your PC and then go to menti.com and put the code 2468967. We invite you all to play the games together so you can get interesting prize at the end of this game. We're still waiting for the participant to come. Please join us by visiting menti.com and input the code 2468967. Okay, we got a lot of players here. Let me share my screen so we can see who are already here. Okay, we have 140 players. We will be waiting for another minute, I think. Let's join. There are 4 questions in this quiz. The questions are all prepared by our speaker today, Richard Bathurst. So if you already watched the presentation, I think you can handle this game. Okay, we have 162. Let's go, let's play. I'm going to start counting down. 15, 14, 13, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Okay, let's play the game. We have 181 participants in this game. I will start the game now. Question 1 of 4. Answer fast to get more points. Why are geosynthetic reinforced soil walls more seismically resistant than other wall types? Is it because of the aspect ratio? Is it because ductility or the strength of the geosynthetics? You have 49 seconds to answer this question. The faster you are, the more points you get. Why are geosynthetic reinforced soil walls more seismically resistant than other wall types? Is it because of the aspect ratio? Is it because of the ductility? Or is it because the strength of the geosynthetics? We have 20 seconds left. Come on. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Time's up. Let's see what is the answer. It's ductility. We have 61 people who are right, but who is leading the leaderboard for this first question? For the first question, the leader is Aflizal Arafianto. Well, can you keep up until the end of the game? Let's see. Here comes the second question. Question 2 of 4. Answer fast to get more points. When do we need to carry out seismic design? Is it after an earthquake has caused damage near our site? Is it for all projects in Indonesia? Or when codes indicate high seismic risk? So what is the question? You have 45 seconds to answer the question. But answer faster and you get more points. "30 seconds left. When do we need to carry out seismic design? Is it after an earthquake has caused damage near our site? Is it for all projects in Indonesia? Or when codes indicate high seismic risk?" 10 seconds left. 5, 4, 3, 2, 1. Time's up. So the answer is when the codes indicate high seismic risk. Let's see who leads the leaderboard for the second question. Ooh. Well, now the leaderboard leader is Shannon Hannah Natalia Desriani. Let's go to the third question. We have 4 questions, okay? Start. Answer fast to get more points. Which method of analysis is adequate for preliminary seismic design and feasibility of geosynthetic reinforced soil walls? Is it wall design method with pseudostatic seismic forces, or 2D FEA with earthquake time history, or 3D FEA with nonlinear soil models and pseudostatic forces? You have 40 seconds left to answer the questions. "25 seconds left. 15 seconds left. Okay. 5, 4, 3, 2, 1. Time's up. So what is the correct answer? The answer is wall design method with pseudostatic seismic forces. Let's see who leads the leaderboard. Let's see. We have a tight competition here. The fastest is with Joyo Prakoso, but not the leader of the leaderboard. The last question. Answer fast and answer right. Question 4 of 4. Get ready. Last question. What is geofoam? This might be the most difficult question. Is it a beer surf in Atlanta? Is it a method of harvesting wave energy? Or is it a lightweight fill? What is geofoam? I think it might be the first one, or I don't know. It might be a hint. Is it beer surf in Atlanta? Is it a method of harvesting wave energy, or is it lightweight fill? You have 20 seconds to answer this difficult question. Ten seconds left. Let's see who wins the game. 4, 3, 2, 1. Time's up. The answer, what is geofoam, it's lightweight fill. It's not pier surf in Atlanta. Sorry for 5 people who answered that. Okay, who is the winner of the game? Let's see. Well, congratulations to Anthony Gunawan. The committee will contact you after this webinar, and congratulations for winning the game with the point of 3,914. Once again, congratulations and thank you for everyone who participated in the game. Okay, maybe Richard, do you want to say a word or two about the game?
Oh, that was, I've never seen that before. That was very exciting. But it also means that there are some people that should not be allowed to design MSE walls.
Yeah, 5 people answer the geofoam has appeared at surf in Atlanta. Thank you, Richard, for making the questions for the game.
Thank you.
Okay. Coming up for the quiz. Sorry, for the winner, you may send the screenshot of the winning page to the committee at INA-IGS webinar at gmail.com. Ladies and gentlemen, we have now reached the end of the event. Before you leave this webinar, we would like to inform you that you can access your e-certificates and the soft copy material from the speaker by visiting the link s.id/info INA-IGS02. Once again, you can access your certificate at s.id/info INA-IGS02. You may also simply click the link on the chat box. After filling the quick survey, you will be redirected to the e-certificates. Once again, thank you for your participation. We hope we can see you at the next event. At last, good evening and stay healthy, everyone.
Are you still there, Mike?